this chapter in the last class. So far in the previous chapter, we discussed about the primary pollutants, the health effects created by them, mechanism that is involved to form the primary pollutants in IC engine, and what are all the factors, engine design and operating variables that influence primary pollutant formation in IC engine. Now, with that understanding, we are now moving and discussing the control methods, pollutant control method. Again, the focus is only on the primary pollutants. Okay, we are not discussing the other species emitted by engine. These four species, since they create severe health effects, we are discussing control methods for these four species. So as discussed, there are two broad classification of the control method. One is in-cylinder method that reduces pollutant inside the cylinder itself. Then there is after treatment control method, which reduces pollutant level in the engine tailpipe or exhaust pipe before the pollutants are discharged into atmosphere. In-cylinder method, no need for any other additional devices or control. Whereas for after treatment, you need to have additional devices that needs to be fixed in the engine tailpipe. Using those devices, which are designated as after treatment devices, it is called after treatment because you are allowing the pollutant to form in the engine cylinder and you are treating or reducing those pollutant in the tailpipe before the gas is discharged into atmosphere. That's why it is called after treatment. You allow it to form and treat it afterwards. So this after treatment method needs additional devices that needs to be fixed. So it means there is additional cost involved with after treatment control method. The current practice in achieving emission mandate, which I am going to discuss in the last chapter, is we have to use both in-cylinder and after treatment. Otherwise, it's very difficult to meet the current emission mandate. So a combined in-cylinder after treatment control method is generally adopted. So in in-cylinder strategy, we focus on design and operating variable as well as fuel will also play a big role in controlling pollutant in the cylinder. Already we discussed this design and operating parameter, how they influence pollutant formation. So we'll have a quick summary of all these parameters that will help us to control pollutant levels in the cylinder itself. This is what is an in-cylinder strategy. Here we are going to discuss about thermal and catalytic method. Thermal method is relying on the temperature. Okay, so the temperature levels in the exhaust is going to be utilized to control the pollutant. This is ineffective method. Generally, this is an old method and ineffective. We follow catalytic route, meaning we use different catalysts to effectively control the pollutant levels, okay, in both SI and CI engine. So this is the current method that we follow in after treatment devices. We need to use some catalyst. So these are all the contents we are going to discuss. In the last class, before we discuss about the pollutant control method, I discussed about the typical exhaust gas condition in terms of composition and temperature, which is significantly different in SI and CI engine. SI engine, you have higher exhaust temperature because operating temperature itself is high. And the products are having more rich mixture combustion because you run close to 1.1, 1.2 is on the richer side. So you will have more rich products of combustion in the exhaust of SI engine. Whereas in CI engine, the temperatures are less, typically 100 to 500 because operating temperature itself is less in CI engine since we use XSR up to 50%. For the same reason, you won't have any rich products of combustion, rather you will have lean products of combustion in the exhaust. So the exhaust conditions are different. It is important to understand this exhaust condition in order to incorporate suitable after treatment method. So with that information, I will continue now about the strategies or control methods available in cylinder and after treatment. Okay, so here I have provided a summary of in-cylinder and after treatment control method that are available to reduce the primary pollutant. So as said, the in-cylinder method target to optimize engine design and operating variables inside the cylinder so as to reduce the formation rate of pollutant, also improve the oxidation rate of pollutant so that overall pollutant level will be less in the tailpipe. So you have various options under this in-cylinder control method. Those are listed out here, and I have also indicated in which engine it is effective, whether it is for SI, CI or for both. Okay, so these are the in-cylinder control method, starting with exhaust gas recirculation. So I will give more detail as we move on. So here, let us just look at the available methods and where it is used, whether it is SICA or both. Exhaust gas recirculation is one of the most effective control method for oxides of nitrogen. Okay, so and you can adapt this method both for SI engine as well as for CI engine. It's one of the most effective oxides of nitrogen control method, in-cylinder control method, meaning by doing exhaust gas recirculation, you can reduce NOx levels in the cylinder significantly. The second option, in-cylinder option, is combustion chamber optimization. We already discussed in chapter 3 the combustion chambers that are available design of combustion chambers for SI and CI. By carefully optimizing the combustion chamber, you can reduce primary pollutant both for SI and CI engine. We will discuss this. Okay, so this is an effective in-cylinder control method. Third one is operating variable injection parameter optimization, and this is applicable only for CI engine, not for SI engine. In SI engine, injection parameters do not have any significant role in controlling primary pollutant, whereas in CI, they are having a significant effect. So when I talk about injection parameter, if you recollect, we have already discussed about injection timing, injection pressure. So here I will also talk about something called split injection or multiple injection. So this is again, these are the options you have in terms of injection parameters, injection timing, injection pressure, split injection. Okay, these are the options you have to control primary pollutants in CI engine. So, and this is also one of the most effective method to control the pollutant level. I'll give more detail as we move on. Next one is a design-based option, variable valve timing. So you can design a system that can vary the timing of the valve. When I say valve timing, it is intake, exhaust valve, open and close timing. So you can use a variable valve timing system wherein you can change the timing of the intake and exhaust valve when the engine is running. This is what I mean by variable valve timing, and this method is also found to be effective to control both NOx and HC. I will talk about it, and this can be adapted both for SI engine and CI engine. Okay, this is also an effective method to control primary pollutants like NOx and HC for SI and CI engine. The next in-cylinder option is downsizing and supercharging. It's applicable for spark ignited engine. Downsizing is about reducing the engine size, that is displacement volume. So you know the power rating of the engine is based on the size. When you reduce the size, the power rating will come down. Now to achieve the same power rating, you need to do supercharging. This is what I mean by downsizing and supercharging. Reducing the engine capacity and achieving the rated power by using supercharger. And this option is available for SI engine. It's also an effective primary pollutant control method that we will discuss. Fuel modification. Instead of running engines, IC engines with conventional fuel, that is diesel for CI engine and gasoline for SI engine, you can also run the engine with several alternative fuel. And using alternative fuel is found to be one of the effective in-cylinder control, pollutant control method for both SI and CI engine. So we'll talk about what are all the alternative fuels that we can use in SI and CI engine so that we can reduce the pollutant level. Combustion mode modification. So here I will talk briefly about running engine in a different combustion mode. Rather than a conventional mode, we'll talk about an alternative combustion mode which is available for CI engine. And this method is very effective to completely eliminate NOx and particulate. You can achieve almost zero level of NOx and zero level of particulate by running engine in an alternative combustion mode. So this is also an effective in-cylinder control method. My current research interest is in this alternative combustion mode. So I'll give some details about this method to reduce pollutant, especially NOx and PM. We get almost zero level of NOx and particulate by running CI engine in this alternative combustion mode. So after treatment method reduce pollutants in the engine tailpipe by having some additional devices which are called after treatment devices. They will be fixed in the engine tailpipe. Using those devices, the pollutant levels are reduced in the tailpipe before the gas is discharged into atmosphere. So we have some devices and operating the devices at appropriate time will help to reduce the level of primary pollutants in the engine exhaust before the gas is discharged into atmosphere. This is what we are doing in this method. That's why it's called after treatment control method. So you have two primary types of after treatment control. One is called thermal route, which is an old method. This is not effective and it's not being currently used, but I will just discuss the principle. Thermal route relies on temperature available in the exhaust tailpipe to reduce HC and CO, and this option is suitable only for SI engine. Why? Because we recollect that the temperature levels in SI engines are high. Exhaust temperature levels in SI engines are much higher compared to CI engine. CI engine exhaust gas temperature is much lower. So catalytic, this thermal route relies on the temperature of the exhaust gas. Okay. Since the temperature of exhaust gas is high for spark ignited engine, we can use this thermal route to reduce SC and CO. Okay, but as I said, this is an ineffective method because you cannot, exhaust gas temperature varies as indicated here. From no load to full load, it varies. It may be as low as 300 degree at low load condition. So when the temperatures are less, that method is not effective. That's why we currently use this catalytic route, meaning we will use some catalysts, and this catalysts are found to be very effective. Using catalysts is found to be very effective, meaning even at a lower temperature compared to thermal reactors, this method is suitable to control all the primary pollutants, both in SI engine as well as in CI engine. So this method is suitable for both SI and CI engine. In SI engine, the device used is called three-way catalytic converter. It's called three-way catalytic converter because it reduces all the three primary pollutant, NO, HC, and CO are the primary pollutant from SI engine. This one device can reduce all the three primary pollutants. One of the most effective catalytic converter that we have for spark ignited engine. Whereas for diesel engine, you need to use different devices. Unlike SI engine, diesel oxidation catalyst is used to control HC and CO levels in a CI engine. Lean NOx trap or selective catalytic reduction method is used to control NOx in CI engine. Lean NOx trap is generally used for light duty or small diesel vehicle. Selective catalytic reduction method is generally used for heavy diesel vehicle. I will talk more about it as we move on. And other device is diesel particulate filter. This needs to be used to reduce the particulate level from CI engine. So you could see that after treatment control is complex for CI engine because you need to use different devices for controlling different pollutant. DOC, diesel oxidation catalyst, is used for HCCO control. Lean NOx trap or SC or selective catalytic reduction is used for NOx control. For particulate control, we need to use diesel particulate filter. So you are using multiple devices, unlike SI engine, wherein you use only one device to control all the pollutant. Here we need to use multiple devices to control different pollutants, primary pollutants from CI engine. So this is an overview of this control methods in cylinder and after treatment control method that are available. I have just summarized all the available methods here. Now I will give some more final details about these individual methods. Okay, let us start with this exhaust gas recirculation method. Let us look at how it is controlling NOx. So an exhaust gas recirculation method, as the name itself implies that you are recirculating exhaust gas from the exhaust line. So you are tapping exhaust gas, a fraction of exhaust gas from the exhaust line. So this is exhaust manifold or pipe. This is intake manifold. So you are actually tapping a fraction of exhaust gas by having a pipe additional line, flow line. You create additional flow line, tap a fraction of exhaust gas from the exhaust line, okay, and then circulate it back to the intake manifold. Okay, so in intake manifold here you have air coming in. So what we are doing by recirculating exhaust gas, a fraction of exhaust gas, you are mixing air and exhaust gas before it is sent to the engine cylinder. So you have a mixture of air and exhaust gas sent into the engine cylinder. In a CA engine, you introduce fuel later on using an injector. If it is a SI engine, you will inject fuel in the port. Okay, so irrespective of the type of engine, you can use this. And you have a flow control valve available here, and this is going to regulate the mixture proportion. That is, the quantity of exhaust gas going into the intake line is being regulated by having a flow control valve in the flow line. That this is called bypass line. So in the bypass line, you have a control valve to control the flow rate. And here we use this to calculate the percentage of how much percentage of gas is recirculated. That is nothing but mass flow rate of exhaust gas divided by total mass flow rate. Total mass flow rate into the engine is the summation of fresh mixture and exhaust gas, total mass. Okay, and in the numerator, you have exhaust mass. Okay, all these are time based, so it's mass flow rate. The ratio of these two is what is percentage of EGR. Okay. So to regulate this flow of exhaust gas from the intake, from the exhaust to the intake, what you need to have? How will you create the flow?
One-way valve should be there.
The valve is there, but to create this flow, what is required fundamentally?
Pressure difference.
Pressure difference. So you need to have sufficient delta P, pressure difference. So you need to have a pressure gradient, meaning you need to have a high pressure here. You need to have a low pressure here. This is what I mean by gradient. If there is a gradient available, then the flow happens naturally. So in a naturally aspirated engine, sometimes you may have a very less pressure, especially at low load and low speed condition. The pressure in the exhaust line will be considerably less. If the pressure in the exhaust line is considerably less, then the delta P will be less. If delta P is less, the flow rate of exhaust to the intake will be reduced. So sometimes you may have to use some external devices like a blower. You have to create the flow by using additional devices like blower, especially when delta P is insufficient to create the natural flow. Okay, this is an important point. The second important point here is with respect to turbocharged engine. So in a naturally aspirated engine, you don't have a compressor and turbine in the intake, whereas in a turbocharged engine, you have a compressor turbine combination as shown here. So turbine is extracting thermal energy. There is an enthalpy drop. You know how a turbine functions. So exhaust gas with a sufficient thermal energy is let into the turbine. Otherwise, the gas thermal energy is lost into the surrounding ambient. You are simply letting out. So by having a turbine here, you are effectively recovering the thermal energy from the gas. That's why this turbocharger is also called waste heat recovery system. Because you are recovering the enthalpy of the exhaust gas before it is let out into atmosphere. So you are effectively utilizing the gas thermal energy, exhaust gas thermal energy, by having a turbine extracting the work in the turbine. Basically, this delta H is converted into W. W is equal to delta H, in a turbine. So you are recovering work, and that work is used to run this compressor. And what is the function of compressor? You have air at lower pressure entering, and the air is let out at a higher pressure. So, and this is entering into engine at a higher pressure. Because of this higher pressure, density is high, meaning with a given volume or capacity, you are actually increasing the mass that goes into the engine, and this will directly reflect in power output. So with a smaller volume, you can create higher power output by increasing density or mass, having this turbocharger. Okay, so what complexity is there in a turbocharged engine is you have two types of complexity in the sense with respect to EGR, exhaust gas circulation. There are two types of EGR here. One is high pressure EGR and other one is low pressure EGR. In a high pressure EGR, you are going to mix exhaust gas with the air here. So this is high pressure EGR. You are mixing exhaust gas with the air, which is already pressurized. So you are mixing exhaust gas with air at a higher pressure. Okay. Whereas in a low pressure EGR system, you are going to mix exhaust gas with air at the inlet to the compressor. Did you get what I am saying? So here in high pressure system, you are mixing exhaust gas with air at the outlet from the compressor. Whereas in a low pressure EGR system, you are mixing exhaust gas with air at inlet to the compressor. Which one do you prefer?
Sir, high pressure should be better.
On what basis?
Because if you're entering more air before the compressor has to do more work. So probably that will lead to a loss of efficiency. That is my understanding.
Okay. Anything else? Any other problem with low pressure EGR? That is mixing exhaust gas here. Does it create any other problem?
Well, sir, one more thing. It will reduce durability of the compressor also because it will operate at high temperature.
So, it will draw more exhaust gas.
What is that?
It will draw more exhaust gases. The control will be difficult.
Control will be difficult. Okay.
Sir,
Anything with respect to durability of the compressor?
That's what I told, sir. It can reduce the durability of the compressor actually.
So it's going to reduce the durability of the compressor because mixing gas with air and compressing it is not an advisable option because exhaust gas is corrosive at high temperature. Okay, it may corrode the blade, compressor blade. So durability of the compressor may come down because of the gas erosion process. Okay, so that's why generally this is avoided and this is being adapted, okay, in practice. So by mixing exhaust gas at the outlet to the compressor is safe, okay. You are not letting exhaust gas to enter into the compressor. So this is preferable, but you have a problem with method 2 also. Can you highlight what problem you will have?
You have to feed the air at the high pressures actually. It should be more. It should be at least equal to the compressor outlet pressure.
Yeah, so just now I said about delta P, creating delta P to create the flow. Now, if you have a compressor and if you are going to mix exhaust gas, so suppose if you have a turbocharger unit here, and if you are going to mix exhaust gas with the air leaving the compressor, air is at a higher pressure, boost pressure. So your gas should be at a much higher pressure than the air pressure, otherwise mixing won't happen, flow won't be created. Okay, so you may have to definitely use a blower. Okay, slightly pressurize exhaust gas, okay, so that you don't have a problem of creating the flow and mixing it with the air that comes out of the compressor at higher pressure value. So this is what you need to look at when you use a EGR for turbocharged engine. In a naturally aspirated engine, there is no complexity except that to create a flow under certain conditions, operating conditions, there will be difficulty. So you may have to use a blower. Either way, you see that using a blower is effective both for any naturally aspirated engine as well as turbocharged engine. Now let us look at the effects of EGR and how it controls NOx. There are 4 important effects of EGR as highlighted here. One is called dilution effect. We already discussed about this. Mixing exhaust with incoming air is going to displace oxygen in the sense it doesn't give enough volume for the air to occupy the available space. Okay, you need some volume for exhaust to occupy, and that space is not available for incoming air. So basically, this is what is mean by displacing air. You are displacing air in the sense you are displacing oxygen. So oxygen level will come down. This is one of the important effect of using EGR. Second effect is called thermal effect.
Sir, sorry to interrupt. Can you just repeat the first point again?
So dilution effect is about when you mix exhaust gas with the incoming air, exhaust gas needs some space or volume in the intake system as well as in the engine. That space is not available for the incoming fresh air. If you don't use EGR, you can consider 2 cases, with EGR, without EGR. Without EGR, the entire space is available for air. With EGR, you have some space required for exhaust to occupy. That space is not available, or that volume is not available for air.
Clear, sir.
So this is a displacement effect which will bring down the oxygen level, and this will have definitely effect on the combustion process. Second effect is thermal effect. Thermal effect is about reducing temperature. Why temperature is reduced? Because the exhaust gas is nothing but the products of combustion. We have already done a thermodynamic analysis. If you recollect, what are the major products of combustion? Major products of combustion are CO2, H2O, N2. All these are inert species, especially CO2 and H2O are triatomic gases. These triatomic gases have very high specific heat. Right? The problem with high specific heat component in the combustion system is they will act as a heat sink. You know thermodynamic meaning of heat sink. Sink is about something that absorbs temperature and doesn't allow the temperature to rise, something that absorbs thermal energy and doesn't allow the system temperature to rise. So having high specific heat component will result in drop in temperature because of the heat sink effect. They absorb thermal energy released during combustion and doesn't allow the temperature to rise. So these two are the important effects of recirculating exhaust gas, the oxygen, drop in temperature due to dilution effect and thermal effect. There are other two effects which are having minimal effect, I will say, compared to the first two. One is called chemical effect. Chemical effect is because of the species, recirculated species participating in some chemical reaction. One of the important chemical reaction is dissociation reaction that will take place with CO2 and H2O. These species will dissociate and form, for example, if you take CO2, it is going to dissociate and form CO and half O2. And any dissociation reaction is an endothermic reaction. So this needs some temperature. So there will be drop in temperature because of dissociation reaction. Similarly, H2O will dissociate and form H2.5 O2. So you see that they are leading to other species because of this chemical reaction, CO and H2. That is one effect. Second effect, these reactions require higher temperature, so they absorb thermal energy. This is opposite to combustion process, where thermal energy is released. Here, thermal energy is absorbed in any dissociation reaction. So because of this, there will be drop in temperature because of the chemical effect due to absorption of thermal energy by these species. But this is generally a minor effect. As I said, the drop in temperature is not so high compared to the effect that you create here due to specific heat of this component. The last one is density effect, wherein mixing exhaust gas at a higher temperature. So you know exhaust gas is at a higher temperature. If you mix it with incoming air, which is at a lower temperature, what will happen to the mixture temperature? It's going to be high. When mixture temperature is high, what will happen to density?
Increases.
It will drop, sir. It will drop.
It
Sorry,
won't
increase in
increase.
temperature, it will drop.
Yeah, you can use a simple equation of state, rho RT, right? When this is high, this will be less, okay? So density will drop, okay? So when density drops, what do you mean by drop in density? Density is mass per volume. When I say volume is always fixed, constant. When I say drop in density, it will reflect in the mass. Mass that goes into the cylinder is going to drop. This is opposite to what we have discussed for supercharging. Supercharging and turbocharging you are doing to increase the mass that goes into the cylinder, right? Here opposite effect is happening because of drop in density. And this is one of the effect of adding EGR to the fresh incoming air. Your density will drop, mass will drop. To avoid that, this is again a minor effect. Why I say minor effect is you can cool the exhaust gas by using a heat exchanger before it is mixed with the incoming air. So what I mean to say here is use a heat exchanger here, reduce the temperature by circulating a coolant, reduce the temperature of exhaust gas before it is mixed with the incoming air. Okay, so it is an addressable problem. Having a heat exchanger, reducing the gas, you can retain the density of the incoming mixture, meaning that you can avoid the drop in density and drop in power output. So the first two effects are dominant. O2 is reduced, temperature is reduced. You know what will happen if O2 and temperature are reduced with respect to primary pollutant, what will happen?
So when NOx will reduce, sir.
So that's why I say that this is one of the most effective method to control NOx. Oxygen is less, temperature is less, that will directly reflect in drop in NO. Okay, so NO levels will be considerably reduced. That's why people use this EG or exhaust gas recirculation. But what will happen to HC or CO?
C will increase, CO will increase. What you are managing? So it's very call for
Both will increase.
I could see some feedback coming out. I hope you don't have any disturbance in attending the class. This is what I asked earlier also. Right? Are you able to follow without any disturbance?
Yes, sir.
Yes, sir.
Why I'm asking all this is very important. You need to be focused to grasp what I am talking. If something else is going on there, you cannot grasp. Okay? That's why I'm ensuring that you have the required class ambience. So you will have drop in NO. That's why EGR is effective method. But you have other effects, especially HC, CO, and particulate will increase because temperature is less, oxygen is less. Drop in temperature, drop in oxygen will reduce the oxidation rate of HC, CO, as well as particulate. So generally, EGR level, there is a upper level or a cap. Generally, people won't use EGR above 20%. If this is increased beyond 20%, there will be sharp rise in HC. Power output will come down because you have a displacement effect. Okay, power output will come down. Fuel economy will also come down. Engine is going to consume more fuel if you use high EGR. So you have to be cautious in handling the EGR value percentage. Okay, there is upper cap for controlling NO. You cannot rely totally on EGR, right? There is a cap here because there are other effects, detrimental effect on the engine in terms of poor fuel economy. Other pollutants, primary pollutants will increase.
So typically, what is the cap? What is the percentage of EGR that is allowed?
I said 20%. In a conventional combustion mode, we won't go generally beyond 20%. It will be kept below 20%.
Okay, sir. Thank you.
But if you are running engine in alternative combustion mode, you can go above 50%. Okay. I will talk about it as we move on. Okay. So, but in conventional combustion, it's not advisable to go beyond 20% EGR. The second one is combustion chamber optimization. We have already discussed about this when we discussed the factors influencing pollutants. Okay, previously, I'll just a quick recap. In combustion chamber optimization, what we are doing, I have summarized here both for SI engine and CI engine. What we are doing here, yeah.
Sir, one doubt, sir. If we are opening the EGR, it will unstable our combustion, no, sir.
No, that's what I said here. The combustion will be unstable. Yes. Combustion will be unstable. That's why I say that HC is, when I say HC is increasing, it's because of unstable combustion. Combustion deterioration will result in high HC. HC is a product of incomplete combustion, partially oxidized combustion, right?
Yes, sir. Yes.
Combustion quality, combustion quality will deteriorate. That's why fuel economy is poor. Your engine is going to consume more fuel.
Okay, sir. Okay. If this will more impact in diesel engine only, correct, sir?
Both SI and CI engine.
Okay, sir. Okay.
SI engine, why? Because oxidation rate will come down because there is a drop in temperature, right?
Yes, sir. Yes. Because yes, compared to diesel, petrol, already temperature will be more now, sir. If how it will be the
temperature will be more if you don't use EGR. We are considering two cases, one with EGR, other one without EGR. Without EGR, your temperature will be much higher. Oxidation rate, all these are time limiting cases. Okay, you have very limited time. Even a small drop in temperature will have an impact on the total HC level because oxidation rate will come down. That's why I use the word rate. Limited time is available in the engine operating cycle. Okay. Even a small drop in temperature due to EGR in SI engine will have an effect on oxidation rate.
Sir, in this case, if NA engine, NA engine, if we use EGR, there will be no turbocharger, intercooler will be there.
No, irrespective of intercooler or irrespective of whether it is a NA or a turbocharged engine, what I mean to say is if you recirculate exhaust gas, there will be drop in temperature. One of the important effect, thermal effect. Because of drop in temperature, there will be drop in oxidation rate of SC. That will shoot up the SC value.
Okay, sir. Okay.
So SC level will increase, definitely.
Okay. Okay.
So the second option is combustion chamber optimization, which we have already discussed. So you know, in SI engine, when you optimize combustion chamber, one of the objective is to increase turbulence. The second objective is to reduce the surface to volume ratio. Why we prefer to reduce surface to volume ratio?
To reduce the heat loss.
Yes. So this is done to reduce heat loss. When you reduce heat loss, it will reflect in high thermal efficiency. We have already discussed about this. So when we optimize combustion chamber, we will look at these two aspects. One is increasing turbulence level by creating swirl and squeeze. Other one is reducing surface to volume ratio so that you can reduce the heat loss, increase thermal efficiency. So this is what you do with combustion chamber optimization for SI engine. Now we are looking at how it affects the pollutants, primary pollutant. In SI, you have SC, CO, and NO, and this is what is the effect. When turbulence is increased, burn rate is high. Higher burn rate, higher will be the temperature. So NO will increase. Higher temperature help in better oxidizing HC and CO. So HC and CO levels will come down. This is the effect of combustion chamber optimization in SI engine. It will lead to high NO, very less HC and CO. You know, all three levels are high. SC, CO also needs to be controlled. So through combustion chamber optimization, we are actually effectively reducing HC/CO level, but there is a, I would say that detrimental effect of high NO, and that needs to be taken care by some other method. CI engine, if you look at, when we design combustion chamber, the major criteria is improving the mixing rate. Air fuel mixing needs to be enhanced. This is how, this will be our primary consideration. This is done by increasing swirl, increasing squeeze. So this is a primary consideration when we design combustion chamber for CA engine. Now, because of increased rate of mixing, you will have a high burn rate. Okay, high burn rate in the sense temperature is high. When temperature, there are two effects with high burn rate. One is higher temperature. I mean, there are two effects of improved rate of mixing. One is increased burn rate, higher temperature. The other effect is it will reduce the local rich region, because you improved mixing will lead to more homogeneous mixture. So you are reducing the local available rich region. So what I mean to say here is there are two terms here, global and local. Because of mixture heterogeneity, always you have a difference in the global and local. But when you improve the mixing rate, this inhomogeneity is going to come down, meaning the gradients of different fuel air mixture inside the cylinder is going to reduce. That's why I say that you will reduce rich regions inside, fuel rich regions inside the combustion chamber. So this is the effect of creating a combustion chamber with better mixing, fuel air mixing through swirl and squeeze. You have a higher temperature, you have less Phe-rich region. And this will reflect in low HC, low CO, because oxidation rate is improved. Soot also will reduce for two reasons. One, you are reducing Phe-rich region. So soot formation rate will come down. The other important effect is you are increasing temperature. So soot oxidation rate will increase. Overall effect is lower soot. HC, CO, soot, all three pollutant will reduce, but NO will increase because of higher temperature. That should be taken care by some other method. So this is the effect of combustion chamber optimization in SI and CA engine. Next, about injection parameters optimization. Injection parameter optimization, as I said, is applicable for CA engine. In SI engine, we don't have any big role of fuel injection parameter because it's a premix combustion. CA engine, it's directly injected, fuel is directly injected. So when we talk about injection parameters, so we have already discussed about the timing, effect of injection timing and injection pressure previously. If you recollect, okay, injection timing and injection pressure are going to have an effect. So there is one more parameter that you can vary with respect to controlling the pollutants, primary pollutants in CA engines. The method adopted is called split injection. Instead of injecting the entire fuel mass in one pulse, so you have a m.f value fixed. Okay, this is fixed based on what?
Power required.
Power required or load. Okay.
Load.
For a given load, you have a fixed value of m.f. This m.f can be injected at once. Entire fuel mass can be injected at once, or it can be injected in pulses. So here you have one injection. This is what conventionally is being followed. But what you can also do is, instead of injecting at once this entire mass, you can split the mass and inject it in, say, 2 pulses or more than 2 pulses. So we use the word pulse. Okay, 1, 2 or more pulses. Okay, instead of injecting entire mass at once, you can split it and inject it in different pulses, meaning this m.f is going to be divided based on how many pulses. You can go up to 5, 6 pulses also. Okay, so you are going to divide this m.f into n number of pulses, and you are going to introduce them at different timing. This is what I mean by split injection. Split injection is found to be very effective to control all the 4 primary pollutants from diesel engine. You can reduce NOx, you can reduce particulate, you can reduce SC, you can reduce CO. Now let us see how it is doing all this. So when I say you are splitting the total mass into n number of pulses, the first pulse is going to create the delay time, right? Since we have a reduced first pulse or reduced mass in the first injection, you will definitely have a shorter ignition delay time. Okay, because you are injecting less in the beginning, you are not injecting more, right? You are not injecting entire mass at once. Rather, the quantity to be injected in the first pulse is less. Okay, because of this, the ignition delay time will come down, since you are not injecting more, and the mass that is injected during the delay time is also coming down. Since this is coming down, what will happen to temperature? Premix burn is going to be coming down. So you know the intensity of premixed phase combustion is dependent on the delay time. When delay is more, you will have more intense premix combustion. Since delay time is less, you have a less premix burn. I already told you that the temperature, peak temperature is reached during the premix burn. When premix is less, what will happen to temperature?
It will come down.
Will come down. So this will directly reflect in NO levels. Thermal NO formation rate will come down. Since you have divided the pulse and you are injecting less at once, okay, the delay is less, and that fuel injected during the delay time is also less. Premix burn is less. Due to less premix burn, there is a drop in temperature that will reflect in drop in NO. Now let us see how particulate is coming down. Particulate is coming down because of better mixing. You are dividing the total pulse into n number of pulses, and you are injecting only less quantity at a given time, meaning the mixing of fuel with the air is going to be much, much better than introducing all the fuel with one pulse. Did you get what I am saying?
Yes, sir.
So mixing is better. Better mixing will directly reflect in reduced rich region or mixture inhomogeneity. Mixture inhomogeneity will come down when you have a better mixing of fuel and air. Okay, so rich region will come down. Formation rate of soot will come down. Formation rate of CO will also come down, because CO formation is primarily linked with the rich region or insufficient oxygen. So you have less soot, less CO, less NO because of lower temperature effect, less soot and CO primarily due to better mixing, and less rich regions in the cylinder. SC will also come down because if you recollect the mechanism of SC formation, one of the important mechanism is over mixing. And over mixing is dependent on ignition delay time, right? So when you will have more over mixing when you have a longer delay time. So here, since ignition delay is less, the over mixing is also reduced. That will reflect in less SC. So all the 4 primary pollutants in a CA engine can be reduced if you go for split injection instead of single injection. Okay, next we have this variable wall timing. I have already discussed about this when we discussed residual gas fraction in the previous chapter. I will just extend the discussion here, and this method can be used to control NOx and SC both for SI engine as well as for CA engine. So what we do here is we are going to control valve timing dynamically when the engine is running. So you know, with respect to TDC, this is where intake valve is opening, and intake valve will close here after the BDC. When the piston moves from BDC, the intake valve will be closed. exhaust valve open here before the piston reaches BDC during the expansion stroke. Near the end of expansion, this valve will be open, and valve is closed when the piston is moving down, okay, during the exhaust stroke. I mean, when the piston is moving down during the intake stroke. Okay, so during this period of time, from here to here, both intake and exhaust valve remain in the open condition. And this period is called valve overlap period. What is happening during the overlap period? We have already discussed that you have intake being open and exhaust valve is also open. Fresh charge is entering, exhaust gas is leaving. Okay, fresh charge will enter into the engine with some velocity. Okay, and this velocity will help in clearing exhaust gas from the cylinder. This is what is scavenging. So we intentionally keep both the valves open for some time, primarily to achieve this scavenging, because this helps in clearing or removing exhaust from the cylinder effectively. So to carry out this scavenging process, we keep the overlap period, valve overlap period, okay, so that incoming fresh mixture enters at some velocity, and that velocity helps in clearing exhaust gas from the cylinder, engine cylinder. Okay, so by varying this IVO or EVC time, you can vary the valve overlap period, meaning you can vary the scavenging, effectiveness of the scavenging. Right, so you may retain more exhaust in the cylinder, or you may retain less exhaust in the cylinder. Basically, this is affecting the residual gas fraction. Okay, if you retain more exhaust gas, which pollutant will get affected? Which pollutant can be reduced if you increase the residual or products of combustion in the cylinder?
NOx will come down.
NOx will come down. But what will be the other effect of this?
The CO and the SA will increase.
CO, SC, and particulate will increase. Okay, there is a trade-off. Suppose if the NO levels are very high, you retain more residual. If NO levels are less, okay, you don't retain more residual, clear the residual, because this is also going to affect the power output of your engine. That is one effect. And second effect, SC levels will be very high. So generally at low load, you will have a problem of high SC because oxidation rate will come down. So this is generally high at low load. And NOx is generally high at high load because you are burning more and you are increasing temperature. So at high load, NOx will be high. So what you do is you retain more residual at high load so that you can reduce the NOx level. You retain less residual at low load so that you can avoid very high SC levels in the tailpipe. So based on engine operating condition, you can vary the overlap period in such a way that either you can retain more residual or less residual. Accordingly, you are controlling this NO or SC levels in the engine exhaust. So this is one of the way that you control valve timing, and thereby you control the pollutant level in the engine exhaust. The other effect here is about varying this IVC timing. IVC is intake valve closure timing. What is this process? After the intake valve is closed, what is the process happening in the engine?
Compression. Yeah.
So you are compressing the charge. So when you look at how you calculated compression ratio is based on total volume, okay, divided by clearance volume. So this clearance volume is volume when the piston is at top dead center. Total volume is VD, displacement volume, plus clearance volume, okay, which is a volume and TDC. So basically we calculate compression ratio based on the dead volume, TDC and BDC volume, but actually compression won't start here. When the piston moves up from BDC, compression process is not going to start here. Rather, when the compression will effectively start?
After the inlet valve closes.
After inlet valve is closed. Because until this point of time, during this period of time, the valve is in the open condition, some charge is entering. So there is no effective compression until this point of time. Only after intake valve is closed, you will have effective compression in the engine cylinder. So there is something called effective compression, and there is an associated compression ratio. So effective compression starts only after the intake valve is closed, and you should calculate volume based on this, not based on this. Okay, so this is called effective compression ratio. So by varying this IVC timing, you can have the intake valve close here or here. By doing this, you are varying the effective compression ratio. Suppose if you close the valve here, what will happen to effective compression ratio?
It will reduce.
If you close the valve here very close to BDC, the compression effect is more, right? So effective compression will be high. Can I say that the temperature will be accordingly higher here and lower here?
Yes, sir.
So you are changing the in-cylinder pressure and temperature condition by varying effective compression ratio. Okay, and this is done by varying the intake valve closure time. Either you can advance it with respect to BDC or you can delay it. When you delay it, the temperature is going to be less because there is less compression. So this is one of the methods that you can use to control NO. Suppose if NO levels are high, to reduce NO, you can reduce the effective compression ratio so that the temperature is less.
Sir, to repeat whatever you told, so essentially if IVC is more advanced from BDC, my effective compression ratio reduces and temperature reduces. If my IVC is more close to BDC, my effective compression ratio is more and temperature is more, correct?
Yeah, yes. So it all depends on when you start the effective compression process. You can even start at BDC. If you start at BDC, the compression effect is more. Okay, temperature will be high. If you move away from BDC and start the compression process, the temperature in the cylinder is going to come down.
Will we do that? Will we try to be more close to BDC?
If you try, no, under certain conditions, right? For NOx, from the primary pollutant or NOx control point of view, you will have to delay the process.
Yes, noted. Yeah.
Okay, you will have to delay the process. But please note that by delaying the effective compression, you are also reducing the power output because you are compressing less. Okay, always there is a trade-off. You need to carefully optimize. Okay.
Yes, sir. Noted.
So, Professor, sir, ideally this wall variable wall timing or wall overlap is not recommended at low speed, right, sir? Low speed and low load. And
yeah, low load is not desirable to have a high overlap or retaining more exhaust gas, because that will have an effect on HC level. HC will be very high.
Right.
So you have to have a closed loop sensor, monitor the pollutant level. If HC is very high, don't retain more exhaust in the cylinder. If NO is very high, retain more exhaust in the cylinder.
Noted, sir. Thank you.
Sir, in this case, slow speed engine, it will be benefit, sir, if we do like that.
Okay, speed, how it will benefit our, so I just talked about load, not speed here, because I said that low load, you will have high HC problem. Speed, how it will affect is, speed will affect the inertia of the incoming charge. For example, if you are running engine at a higher RPM, the inertia of the incoming charge will be high. Did you get what I am saying? The flow velocity is also dependent on the suction effect in the engine cylinder. Do you agree?
Yes, sir.
When engine runs at high RPM, suction effect is less because, suction effect is more because piston is also moving at high velocity. During intake, the rate at which the piston moved on, this velocity is also high when this is high. Okay, when this is high, the suction effect is inside the cylinder is also high. So the charge will enter with more velocity, more incoming velocity. Okay, when the charge enters, so what you should think here is when the piston is moving up, I'll just take 2 minutes. It's already time up. I'll just complete this.
No problem, sir. Anyway, we don't have a next class. We can.
Okay. So what I'm saying here is when the piston moves down at higher velocity, the charge will enter at higher velocity. Okay, and the inertia of the charge is also high. this will happen at higher RPM. When the piston is moving up, so after it reaches BDC, it's going to move up. So when the piston moves up, you have a valve in the open condition. So the charge is entering with some velocity, piston is moving up. So you know that the upward movement of the piston may cause the charge to go back, because you have some effect due to the upward movement of the piston, okay? And you are compressing the incoming charge. There is no effective compression until the valve is closed. That is different. But since the piston is moving up, it is trying to push the charge in the upward direction. But charge is coming down, right, in the downward direction, since the valve, intake valve is in the open condition. So there is a threshold limit up to which the backflow cannot happen. Okay, the backflow of charge will happen if the piston ram effect or upward effect is more. Okay, and this needs to be overcome by the inertia of the charge. If the charge enters at high velocity, the inertia will also be high. Did you get what I am saying? Then the backflow won't happen. At low speed, this inertia is less because piston is moving at low velocity. But at high speed, this inertia will be more because piston is moving at high velocity. So the reverse flow will be less at higher speed condition. The reverse flow may happen at a higher at low speed, because at low speed the flow inertia is going to be less. This is the effect of the speed. Whatever I have discussed earlier is load effect. How the speed affects the flow process is the speed affects the inertia of the incoming charge. So when there is an upward movement of the piston, you can expect some backflow. Okay, and this backflow can be avoided if the incoming charge has a high inertia. Okay, and this will happen at higher engine RPM. Higher engine RPM will have high inertia, so you can delay the intake valve closure timing. At low speed, you have to advance the intake valve close timing, otherwise you will have a backflow of charge. Did you get what I am saying?
Yes, sir.
So based on the speed, you also have to do the timing change, wall timing change, because it may also result in backflow of charge, fresh charge into the manifold. It won't allow the charge to enter and fill in. Okay, basically intake process is a filling in process. So you have to carefully fix the IVC timing because it should not cause any backflow.
So if we compression send also, this backflow will happen, correct, sir? Some turbocharger, anything if we keep.
Turbocharger will help because you have a boost pressure, you have some benefit. Some benefit in the sense the incoming charge has more mass. More mass means again more inertia.
Correct.
There are two things that will decide. One is the suction effect in the cylinder, that is going to fix the velocity. The other effect is due to boost pressure. With boost, you have more mass.
Correct.
Okay. Okay, so I will just stop here. Downsizing and supercharging. Basically, in downsizing, you are reducing the displacement volume (VD). Okay, so that is what is downsizing. When you reduce capacity, you know the power output will come down. So basically, in downsizing, we are reducing VD. But to bring back the power, you do the supercharging. Okay, by doing supercharging, you are retaining the same power. So power output is retained. Retained in the sense same as a larger capacity engine. So downsizing, you reduce capacity, power may come down. Because you are doing supercharging, you are retaining the same power output. So generally downsizing is done along with supercharging. What is the advantage in terms of primary pollutant? The flow losses and friction losses will considerably. Say downsizing, I am reducing D, I am reducing L. Bore and stroke length are reduced. By doing this, you will have a considerable benefit in the friction. Okay, friction losses will come down. Since the size is less, the flow losses will also come down. This will directly reflect in better fuel economy. By reducing size, you will have a better mileage, a better fuel economy, meaning you are consuming less fuel for producing given power output. That will reflect in low SC, low CO, low CO2 also. It's not a primary pollutant, but CO2 will also come down because you are burning less fuel to produce a given power output. Okay, so downsizing and supercharging is beneficial for spark ignited engine. from the perspective of controlling HCCO and CO2. So I stop here, it's time up. I will continue this in the next class. If you have any questions, you can ask.
Professor, sir, I have a question, right?
Yeah.
Regarding that, you have told that NOx, if you take the NOx emission distribution for the SI engine, 70% is NO and 30% is probably the NO2.
NO2.
That is because of high temperature level in the in cylinder for the SI engine. Whereas in the CI engine, the ratio is like NO is less and NO2 is more because of high level of oxygen present in the combustion
No,
chamber.
NO is always less. For SI or CI, it doesn't matter. NO is always high. In SI engine, NO2 is negligible. In CA engine, it is not negligible. It is around 10 to 30%. The remaining is NO. NO level vary between 70% to 90%. So NO is always high compared to NO2.
So suppose, sir, if I'm making an engine of 500 cc, one is SI engine, one is CI engine. So typically, what will the value of total value of NOx in SI and CI? Just the approximation I'm telling.
Irrespective of the engine type, the split is same. If it is SI, it will be 97.3 or less than 3%, 97% NO, less than 3% NO2 for SI. For CI, based on the operating condition, it will slightly change. That is, NO will be 70% to 90%, 10 to 30% will be NO2.
So that means the total NOx emission will be almost similar for SI and CI, right, sir?
Yes, this is what I said in the beginning also, right? NOx is comparable for SI and CI.
Right, sir. Still, it is being told that CI engine is having more NOx compared to SI. Why it is so? Like NOx control is difficult in, like problematic in CI compared to SI.
No, NOx control, why it has become a complex problem in CI engine compared to SI engine is, in CI engine, you have a trade-off with particulate. SI engine, you don't have a particulate problem. So you have a flexibility to adopt several NOx control method for SI engine. You don't have that flexibility here in CI engine because whatever you do to control NOx, you are increasing particulate emissions.
Okay, sir. No, it's
This is where the problem comes because of the trade-off between NOx and PM. But NOx levels are almost comparable with SI and CA. SI, you don't have PM control problem. In CA, you have a control problem. Also, there is a trade-off between these two.
Got it, sir. So levels are similar, but trade-off is creating a problem for CA.
The trade-off is what is complicating the problem of emission control in CA engine. That's the core problem in CA engine. You have a NOx PM trade-off, which is what is the cause for all the emission control technology cost is always high for CA engine.
Thank you, sir. Thank you so much. Noted.
Okay, fine. Okay, so I'll stop here. Tomorrow also we shall meet at 5 o'clock instead of 6 o'clock. Okay.
Okay, sir. Thursday and Friday we will continue as it is, sir.
I will see how much it goes for tomorrow. Okay, we will definitely have Thursday. Friday I will see.
Okay, okay, sir. Thank you, sir.
Okay, thank you. Bye.
Thank you, sir.
Bye.